Hello and welcome back to our little computer building exercise. In the last video, what we did was we essentially created an encoding for the move instruction, which does a very simple thing. It just takes any value that you have and then stores it into one of the slots that we have in our memory. But as I said at the end of that video, this isn't a very interesting computer because all it can do is store values and it doesn't actually compute anything. In order to compute stuff, we need to also encode the add and multiply instructions, and that's what we're going to do in this video. Now, the difference between the add and multiply instruction with the move instruction is that unlike the move instruction, which only had one input, which was a value, and then just stored that into one of the slots, we have an instruction with two inputs. So add and multiply needs at least two things to add or multiply. And so now our instruction is going to change a little bit, and our instruction structure is going to change a little bit. So on a higher level, our instruction, if I were to put it in the same form that this move instruction was here, right? In human form, we would say something like, okay, add my input 1 to my input 2, and then store that into one of the slots. So let's just say slot 0. Okay. But what are these input 1s and input 2s? Well, in the case of the move instruction, the inputs were just values. But for these instructions, we're going to do something different. Instead of adding just raw numbers that we just write in their numerical form, like we won't be doing things like add 3, 4 into a 0. Instead, what we want to do is we're going to add what is contained in the computer's memory. So we'll say something like add S1, S2, and store it in S0. So let's just write a very simple sample program in order to demonstrate what I mean. I'm going to move this down here just so we have a snapshot of our memory. Oops. Okay, so our little program is going to be, okay, so move the number 3 into S1, and after that executes from the last lecture, you know that would mean the number 3 was now stored in this slot. Now let's also move the number 4 into S2, and now we have the number 4. And then in the next instruction, what we're going to do is we're going to use the values that we just stored, which are S1 and S2. We're going to add them and store them in S0. And 3 plus 4 is 7. So this is what our memory would look like right after the add instruction finishes. It will add the two numbers in S1 and S2 together and store the result in S0. So, just like before, we have the question, how do we actually represent this to a computer in ones and zeros? Well, let's look back. So we already have the encoding for the instruction. So let's just map this out right here. So add is 0, 0. That is the encoding we've decided for all our instructions, and if it were multiply, it would be 0, 1. S1, well, we also did the encoding for that when we did the move instruction, if you remember. So here they are. So it's just the binary representation of the index of the slot. So what are we storing here? Sorry, we are adding S1, so that means we represent this with 0, 1, to S2, which means we represent this with 1, 0, and we store that in S0, which means 0, 0. And now if this, computer / processor memory that we've just kind of defined as an example were to exist, we could feed these instructions into it, of course in their binary form, and it would very much just calculate the sum of 3 and 4. And I think this is pretty cool because this is actually very close to what a real computer does, is it just crunches these binary numbers together, and because of how we encode them and how we interpret them, and we write programs to interpret them, we can do all these wonderful things with computers like streaming videos and looking at cat pictures. But we'll get more into that later. For now, let's do another example really quickly about for the same thing, and I want you guys to write an instruction to multiply the numbers 5 and 6. Or I guess a series of instructions to multiply the numbers 5 and 6 using the instructions that we've defined here. Okay? And then also convert them to binary format. So pause the video and try to basically do 5 times 6, and let's say and store that into S0. So I will let you guys try that. Okay, welcome back. So just to take up the little problem we have, what do we need to do? First, we need to put the numbers 5 and 6 into our memory, and we do that using the move instruction. So we move the number 5 into one of our slots, so let's say S1, and then we also move the number 6 into S2, and then we just use the multiply instruction to multiply our two terms, which are stored in S1 and S2. So multiply S1 by S2, and as in the problem, it says store that into S0. And of course, the binary representation of that would amount to, okay, so move, the encoding for that is 10, so 10, that's the instruction code. Then the number 5, which is 0101 in binary, and then S1, which is just 01. So that's the first instruction. And then the second instruction is another move instruction, which we represent as 10 with, and this time we're storing 6, so that's 0110. And then we're storing it into the second slot, which is represented as 10. Now, and the last thing we do is the multiplication. So we haven't done multiplication yet, but all you have to do is look up the code. So the code for the multiplication instruction is 01. And then we just have to map out the slots that we're going to use. So we're going to multiply slot 1 by slot 2 and store it in slot 0. So that translates to 01 for slot 1, 10 for slot 2, and 00 for slot 0. And what this will do is, if we change the memory, if this is the program we're executing, we'll move 5 into S1, so there's 5. We will move 6 into S2, so there's 6. And then we'll multiply S1 by S2, which is 30, and then store that into S0. And voila, there we go. So together we've created this very simple multiplying and adding computer that has memory for four different results. And hopefully now you'll be able to see how in the next lecture we're going to write a program that will calculate this 35 by 47 using the instructions that we've just defined. If you want, and if you're brave, you can try and code this program yourself. Except the one rule in order to make this somewhat challenging is you cannot move a number greater than 9 into any of the slots. So the move instruction value here must be less than or equal to 9. So try it out. It might be fun. If not, we'll take it up in the next lesson, and then hopefully everything will become clear.